Go. Good morning, everybody. Welcome to another, I guess, rainy, cloudy morning of Chem 1211 with your host, me, Dr. White. And today we'll be doing the gas law practice problems. We'll also be doing the Molarity Lab. I'll show you how to do that on uh, Beyond Lab Z. But before we do that, Dr. White has to apologize to all of you. I'm sorry. Uh, it turns out, even though last semester I didn't have a trouble, when I looked at it now and from last night, a number of you had problems with the lab that's due today, which you can still hand in up to Sunday. And if you've already handed it in, you're comfortable with it, just ignore what I'm going to say. If you're having problems, what I did is I went and improved it. And it's now in the assignment area. And you can still download this and upload this. What I did was, if you notice where I have, and let me get there's some people with cameras on. Some of you turn on your cameras, please. I'm just seeing a bunch of names. Anyways, use your emoji. Thumbs up, people. Can you see weight of magnesium metal strip on your screen? Use the thumbs up. All right, thank you, Brianna. All right, now, and Zach too. In the previous lab, I called this number 1, B number 2, and so on. I've changed the numbers to letters because there was massive confusion. I'm sorry that when we got down here, number 5, where I had a number sign in front, people were confusing it with this 5, and so on down the line. So what I did this morning was I changed all the numbers here in the bracket here, closed bracket, to letters to help you out. And I've changed this here to letters, where R is this, but just tells you what values you should be using to determine N using this equation. And hopefully that will help you out. Also, and if you've already handled a lab and you're comfortable with it, you don't have to do anything more. But what I did in table 1, which you have to do on your own before I added it, I added converting this Celsius to Kelvin, even though down here, I tell you be sure to use Kelvin, not C. But anyways, that's that. If you have any questions still about this lab, I'm going to stick around after lab today. You have until Sunday. You really should get it today, but because of the confusion and everything, you have until Sunday to get it in. Any questions about that? All right. What I'd like to do now is go through the practice problems for the gas laws and gas chapter. Let me do one thing first. Close this. Close this. All right, thumbs up, people. Oh, I see some faces. Real people are out there. Everybody see? As soon as I get to the top, hang in there for 1 sec. All right, everybody see Chapter 11 gas law problems on your screen? Thank you. All right, now let's look at these. there's something you should know. And let me switch to my whiteboard. This is an important information for test number 3, but you should know the following. 760 millimeters of mercury equals 760 torr, which is short for honoring the great Italian scientist Torricelli, equals 1 atmosphere, ATM. That's awful looking. Let's fix it up. That's better. And this is something important. These are all exact numbers. 760 millimeters of mercury equals 760 torr equal 1 atmosphere. And from this, you can also conclude 1 millimeter of mercury equals 1 millimeter. Not this. Well, it does, but that's not what I wanted to write. That's not what I wanted to write. I'll wake up soon. Actually, I've been working since about 5:30. All right, so if we go back to the problem set, how many torr is 41.5 millimeters of mercury? Use your good buddy, your good friend, unit analysis. And here's what I'm starting with. I'm going to torr. Torr goes on top of the ratio. Then I'm going to convert this to torr. Millimeters of mercury go underneath. That's 1 to 1, so you get the same answer. Now, if we look at number 3, how many atmospheres is 741 torr? Well, you're trying to find atmospheres. You're given torr. And I even wrote it on here in case you forgot it. 760 torr equals 760 millimeters of mercury equal 1 atmosphere. And we start with torr. We want to get to atmospheres. Use your good buddy, your good friend, unit analysis. Atmospheres go on top, torr go underneath. This cancels out. These are exact numbers, 3 significant figures, 3 significant figures. Now, if we look at 4, it is how many torr is 1.237 atmospheres. What are we trying to find? Torr. What are we given? Atmospheres. We start with this. We're trying to get to torr. Torr goes on top of this ratio using your good buddy, your good friend, unit analysis. Atmospheres go underneath. Where do I get these two numbers? 760 torr equal 1 atmosphere. These are exact numbers. Therefore, this is 4 significant figures. My answer is 4 significant figures. And today, Dr. White's going to share some of the fun. And here's one for you. How many atmospheres is 815 torr? Have some fun now. Oh no, he's going to make us work this morning. Bad Dr. White. While you're doing that, I'm going to open up my spreadsheet. And when you're done, either give me a thumbs up on your video or use the emoji. All right, looks like everybody's done. So what do we do? Well, first of all, what are you being asked to find? ATM. What are you given? This number of torr. Torr is pressure. So this is the only thing we have to start with. So I'm going to use it because there's nothing else I can use. And if I can convert this, what units do I want my answer in? Well, we figured that out. It's ATM. Therefore, I'm going to use my good buddy, my good friend, unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. Where do I get those numbers? Right here. And that will be given to you in important information, test number 3. Oh, by the way, I highly recommend before test number 3 or before you really get into studying for test number 3, you open up in the lecture section a Blackboard, test number 3, important information, and you'll see what I give you. Now, when we use unit analysis, atmosphere goes on top, torr goes underneath. Where do I get these numbers? From here. 1 atmosphere equals 760 torr. And notice torr divided by torr, anything divided by itself equals the number 1. And therefore cancels out. I'm left with the right units. And now I can happily go to my calculator, in this case with Dr. White. It's my spreadsheet. I go here. Here's the number I get. However, 815 is 3 significant figures. 1 and 760 are exact numbers. Therefore, I have to round this off to 3 significant figures. Keep the 1, keep the 0, keep the 7. Use the 2 to round off. That's 4 or less. So the answer here is 107. Actually 1.07. Whoa. And that's how you do it. And this is a skill you should have. Hint, hint. Which is why I put it in the practice problems. And here I use millimeters of mercury, but remember 760 torr equals 760 millimeters of mercury equal 1 atmosphere. We're trying to find millimeters of mercury. We're given atmospheres. Here's the atmospheres. We're trying to get to millimeters of mercury, use unit analysis. Millimeters of mercury go on top. Atmospheres go underneath. Where do I get these numbers? Oh, look, someone was nice enough to write on this piece of paper, 760 millimeters of mercury equal 1 atmosphere, 760 millimeters mercury per 1 atmosphere. Atmospheres cancel out. These are exact numbers. 4 significant figures. It's sort of hidden in there, but it's 3.469 times 10 to the 6, 4 significant figures. All right, let's go on to the next problems. And let me remind you of Boyle's law. And Boyle's law is P1 times V1 equals P2 times V2. And P1, and this will be given to you in important information, but I'm going to write it now, is initial pressure, V1 equals initial volume. P2 equals final pressure. And V2 equals final volume. Now, the pressure and the volume in this equation can be in any units. The pressure and the volume can be in any units you're using. So let's go now look at a problem dealing with this. Number 6. And by the way, if you ever want me to do a problem that I'm not doing, ask. Because as you know by now, hopefully you do, there's no such thing as a dumb question, and all questions are good questions in my world. And right now, uh-oh, look out, it's going to sneak out. Awful, awful humor time. You're in my world. No, it's not Wayne's world. It's Dr. White's world. That was pretty bad. See how I'm making you suffer? All right. Thumbs up, people. Do you see if a balloon? Thank you. All right. If a balloon has a pressure of 658 torr and a volume of 1.894 L, L stands for liters, a measure of volume. What's the pressure of the balloon if the volume is increased to 5.133 liters? Well, what are you trying to find? Well, a pressure after you've changed something, which means that's P2. What are you given? The initial pressure is this, P1. The initial volume is this, V1. And the final volume, which is what you're going to increase it to, is this. And now we know, and here's the giveaway, when you have a gas problem, meaning on a test, you use, and you see only pressure and volume involved, it's P1 times V1 equals P2 times V2. And this is an important information, test number 3. And now what are we trying to solve for? P2. Now we're going to do some algebra. Let me go to the whiteboard to do this. Now we want to solve for P2. How do we do that? Well, we've got to get rid of V2. And when two things are multiplied, and you want to get rid of one of those, you divide by that number, because anything divided by itself equals the number 1, which means it's gone. Well, whatever you do to one side, you have to do to the other side. And now V2 divided by V2 cancel out, become the number 1. 1 times P2 equals P2. And now we have P1 times V1 equals divided by V2 equals P2. I like to rewrite it. You don't have to. And that's how you solve for P2. Again, when you have two things multiplied and you want to get rid of one of them, divide by that number, because anything divided by itself is number 1. If I do this to one side, I have to do it to the other. V2 times divided by V2 is 1. 1 times P2 is P2. This is the other side. I just flipped it around. And once you've done the hard part and also identified the variables, here we have P2 equals V1 over V1 times V1 over V2. I put them in there. Notice this is a multiplication division. You get the same number of significant figures in your answer as the number you multiply or divide that has the fewest. 3, 4, 4. What's the lowest number? And time's up. It's 3, which is why our answer has 3 significant figures. Notice liters divided by liters, the units cancel out, and I'm left with torr. And unit analysis, again, is your good buddy, your good friend to make sure that you are on the right track. Now, you might have done it, but I'm going to make you work today. Look at number 7. Can you all read that at the bottom of the screen, all right? Right here. If a piston has a volume of 22.4 liters at 12.34 atmospheres, what is the volume of the piston when the pressure is reduced to 3.567 atmospheres? Your turn. Why don't you try that? If you don't have a calculator, just set it up. What are you being asked to find? What are you given? And what equation do you use and solve for that variable? And just put the numbers in. If you want to calculate them too, you can, because I'm not going to stop you. It's a free country still. Hopefully, a long time still. And when you're done, give me a thumbs up. If you're lost, give me a thumbs up too. I hope you're not. All right, I think everybody's done. Anybody need more time? All right, let's take a look at this now. And number 7, if a piston, that means you have a plunger in a cylinder, like the piston of your car, has a volume of 22.4 liters at a pressure of 12.34. Remember, L is volume, liters, ATM, millimeters of mercury, torr, our pressure. What is the volume of the piston when the pressure is reduced to 3.567 atmospheres? So if we look up here, we're talking about a gas because we're talking about volume and pressure. And all you're dealing with is volume and pressure. That immediately tells you Boyle's law. P1 times V1 equals P2 times V2. We're trying to solve for V2. So how do we solve for V2 using this equation? Well, if I want to get rid of P2, which I do, because I want V2 alone on one side, if I'm solving for it, anything divided by itself equals number one, meaning it's gone. So if I want to get rid of P2, I divide by P2. However, whatever you do on one side, you have to do on the other. And P2 divided by P2 equals number one, and one times anything is that thing, in this case V2. And on this side we have P1 times V1 over P2. Now you don't have to do this, but Dr. White does. Good habits I don't break. This is a good habit for me. And now to solve for V2, all I have to do is put in the numbers for P1, V1, and P2. And let's go back. And notice, oh, I got it right here too. We have the initial pressure. If a piston has a volume of 22.4 and at 12.34 atmospheres, the initial pressure is 12.34 atmospheres. The initial volume, if it has, and which it did, is 22.4 liters. And what is the volume, which we figured out that's what we're trying to find, when the pressure is reduced to 3.567 atmospheres, which means the final pressure, P2. Now that we have this, we've calculated V2 equals P1 times V1 over P2. We put in these numbers. And notice atmospheres divided by atmospheres cancel out. We're left with liters, which is a measure of volume, which is what I'm trying to calculate. So I know I'm on the right track. Now here, 4 significant, 3, 4, I'm in my 3 significant rut again, and that's our answer. All right, let's move on. Now, let's talk about the ideal gas law, PV equal nRT. Now, P is the pressure, and it's always in atmospheres. V is the volume, and that's in liters. N equals moles. R is the universal gas law constant, meaning it's a number that doesn't change. And here are the units, atmospheres, liters per mole K. Now, let's take a second to look over here. Well, let me finish up first. And T is temperature. In Kelvin. Now, if you forget about what units these are, by the way, it's an important information. Test number 3, I give it to you. Students used to have to memorize this. You don't anymore. Thank you, Dr. White. You're welcome. R tells you the units: pressure, volume, temperature, And once you do pressure, volume, temperature, in case you forget what N is, it's moles. So R, when you're given that, which you will be, there is another reminder what units you have. Now, let's talk about PV equal and RT. Dr. White likes PV equal and RT. It's my favorite mathematical equation in chemistry. There are other things too I like, but I like this one. Now, you should know in the winter, the temperature goes way down in Chicagoland. In fact, what was it, 2 years ago when we closed down a couple of days COD? Because it was 2 or 3 years ago, because the outside temperature during the day was like 20 below and the wind chill was some god awful 40 below. And luckily, the president of school then closed it at COD. It's about everything closed. But in the winter, temperature goes down. So your car tires have air in them, a gas. And PV equal nRT tells you that when the temperature goes down in your tires, the volume, the moles in R stay the same. Therefore, the pressure will go down. And I think I remember I told you that story where when I lived in an apartment complex here in the northwest suburbs, and we had a brutal cold snap, and it was a Friday night, and it got down to like 20 below. Next morning, about 7:30, I figured I should go out and run my car around. That's good for the battery because cold temperature affects your battery. I'll teach you that later in the semester. I went out and looked, and I saw my 4 car tires. And I looked and said, oh no, I've got 4 flats. Then all of a sudden, about 2 seconds it took me out. It's cold, PV equal nRT. That's why I better get myself to a gas station, fill up my car tires. And as I told you before, I got there, there was nobody there. Boy, was I lucky. And I'm filling my tires. I'm pretty quick with that, but still, even a minute a tire, 30 seconds a minute, that's 4 minutes. By the time I got to my last tire, I looked up and there were 10 cars waiting to get to the air pump too. Now, in the summer, it gets hot, temperature goes up, and your car tires, which have gas, air, or nitrogen, I use air, I don't spend the extra money to have a dealership put nitrogen in there. PV equal nRT, and the volume, the moles and R stay the same. If the temperature goes up, your pressure should go up. So you should check your car tires. And I don't know if you remember, back in, I think it was 95, summer 95, we had a brutal heat wave in Chicago. I mean, brutal. If I remember correctly, close to 600 people died because of the heat. And because of that tragedy, now in the Chicagoland area, whenever it gets super hot in the summer, they have cooling areas, different cities. I know both ECC and College of DuPage, COD, become a cooling center when it gets hot like that. But anyways, when I was working by Great America, I had a long trip from Schaumburg on the toll roads, and you always saw that whole stretch, especially in the afternoon, you saw cars and trucks pull over with blowouts. Why? Temperature went up, PV equal nRT tells you the pressure goes up and pop. Everybody see number 10? Thank you. All right, let's take a look at this. One thing that number 10 is missing is 15 points. Hint. If you burp 86.75 grams of carbon dioxide, CO2 gas at 545 millimeters of mercury and 34.6 degrees C, then what is the volume of your burp? Well, first of all, if you see something dealing with gas and you have a weight, a pressure, a temperature, or a volume, 3 or 4 things, nothing's changing, immediately you know that's PV equal nRT. Now, what are you being asked to find? The volume of your burp, V. What are you given? The weight of the carbon dioxide you burped. Is there a proper or a better term for burp? I guess not. I guess that's socially acceptable. I guess you could say belch. Nah, I like burp better. The pressure is this value, the temperature is this, and PV equal nRT, R is the universal gas law constant, which you'll be given. Again, I highly recommend you take a look at important information, test number 3 in the lecture folder of Blackboard. Well, if we're trying to solve for V, find it, and we have PV equal nRT, two things multiplied times each other. I want to get rid of the P, pressure. Let me do this real live for you. If I have PV equal nRT, and I want to solve for V, I want to get rid of P. How do I get rid of anything that's multiplied times something else? Divide by that, because A divided by A equals 1. So divide this side by P, but whatever you do to one side, you have to do to the other. And P divided by P is the number 1. 1 times V is V. I have nRT divided by P. And now I just have to figure out what goes in N, R, T, and P. Now, listen carefully. Really, listen carefully now. I got everybody's attention. Oh, hold on. Did I get your attention now? Listen up. Common mistakes on test number 3. Students put these values into P, N, and T. No, pressure has to be in atmospheres. Oh no, we were given in millimeters of mercury. So how do you convert that to atmospheres? This is what you start with. You want to get the atmospheres, you use unit analysis, your good buddy, your good friend. Atmospheres goes on top, millimeters go underneath. I don't have it written here, but we've talked about it. 1 atmosphere equals 760 millimeters of mercury, 3 significant, 3 significant. Now, this is a multiple step calculation. You can either round off at the end or each step. Dr. White calculates both for the test and the final. Yeah, this is going to be on the final. I'll remind you later in the semester. Oop, I gave away 2 secrets. But anyways, here's the number for P in atmospheres. Common mistake, students put in millimeters when they're doing the calculation here. It's wrong. Next, temperature has to be in Kelvin. Yeah, I've been talking about it so much. Let me do something right now. All right, why are we frozen? There we go. Thumbs up, people. Can you see important of the ideal gas law on your thank you? This is in important information. Remember the units here. I tell you what it is. And also here I give you how to do K. Here's important information that will help you out in there. All right, knowing that, we can do Kelvin for temperature, degrees C plus 273. And this one was sort of a trick, and I probably won't do it on the test. When you do an addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right. This has 1, 273 is an exact number. Therefore, this is the correct answer. Should be actually 4 significant figures. Common mistake, students put in temperature in centigrade, Celsius, as opposed to convert it to Kelvin. Wrong. Finally, N is moles. Don't put in grams. Students do that. No, you have to convert it to moles. How do you do that? Here's my grams. I want to get the moles. Use unit analysis. Moles go on top of the ratio. Grams go underneath. Where do I get this information? 1 mole of a compound equals the molecular weight of that compound. The molecular weight of carbon dioxide, 1 carbon, hold on, excuse me, 2 oxygen, add them up, 44.0. 4, 3, this is 1 mole is the exact number, 3 significant figures. And now, and I've calculated 1.97 moles. R from here, 0.0821. Temperature, Kelvin, 307.6. Pressure in atmospheres, 0.717. And if you were able to burp that much, which you can't, you'd get 69.4 liters. I think the volume of the human body is only 61 liters. I might be wrong. So there's no way in the world you can burp that much out of your lungs. Think of it this way. That would be almost 35 2-liter bottles of gas if they were empty bottles. No, your lungs aren't that big. At least mine aren't. Nope, nope, no way. But you got the thing. Now, let me go back and remind you the important thing again. Students put the numbers here right into PV equal nRT. Wrong. Remember, pressure has to be in atmospheres. You're never going to be given it in atmospheres. Volume is in liters. That I'll always give it to you in liters. Number N is moles. No, you're going to get grams, and you're going to have to know how to convert it to moles, which we did in test number 2, and we just practiced now. In case you forgot, top of important information, test number 3, 1 mole of a compound equals the molecular weight of that compound. And T is in temperature, and it has to be Kelvin. Common mistake students put in Celsius. I want to say the old name centigrade, because that's what I got brought up with. But anyways, I corrected myself. So make sure, it's important, that you use the proper units for PV equal nRT. I'm looking at the clock. Yeah, we got time to sneak this in, part of it. If a tire contains 25.67 grams of nitrogen at 26 degrees C and 705 torr, what is the volume of the nitrogen gas in the tire? That's not what I wanted. With PV equal nRT, why don't you solve for V? Just solve for V. Don't think about the numbers. You're given P, N, R, and T. How would you solve for V? Your turn. This will be real quick. Then we'll take a break and come back. All right, don't put in numbers. Everybody done? All right, I see everybody who can shake their heads up and down. And yes, but let me do this real quick. All right, for those who wanted to poll, looks like you're all done. So with that, how do we get P alone? We get rid of, V alone, we get rid of P. Anything times something else, you want to get rid of it, divide by that. Whatever you do to one side, you have to do to the other. This cancels out. V equals nRT over P. And that's how you do it. If I look at the clock, my timing's good. It's time for a break. Come back at 5 minutes, and that would be 9:55. And I'll see you then. I'm going to go stretch. let's get back to work. All right, we're going through practice problems. Let's do a couple more, then we'll do the lab. Today's a real quick lab, so you'll get out of here before at least 2 p.m. No, I'm just kidding. All right, everybody see number 9 on your screen right now? Thank you. Now, let's go through this one. What is the weight of 5.77 liters of oxygen gas, O2, at 101 degrees C, 678 torr? Now, notice we're talking about a gas. We're not changing anything. And what are we being asked? The weight, grams. What are we given? A volume, a temperature, and a pressure. And you were also given, not here, but on the important information, R. This is PV equal nRT. But you need 2 steps. In order to find the grams, you first have to solve PV equal nRT for moles. Then go moles to grams, which you learned in test number 2, or for test number 2. Hopefully you learned it before you took the test. So how do I solve for N? I want it alone on one side. I divide by RT to get rid of it. R divided by R is 1. T divided by T is 1. These cancel out. Whatever you divide on one side, you have to do on the other. So you have PV equal RT divided by RT equal N moles. I just rewrote it, N equal PV divided by RT. Now remember, in PV equal nRT, volume is liters. Oh, yay, we're given that. Temperature is degrees C. You need it in Kelvin. And P pressure should be in atmospheres, you're in torr. So first, here I convert temperature from Celsius to Kelvin, degrees C plus 273, put it into 101, get 374. Okay. I want to go from torr to atmospheres. This goes on top. This goes underneath. 1 atmosphere is 760 torr. This is the atmospheres. And now I can come in here. My pressure in atmospheres is this. My volume, which should be in liters, I can put in there. R is this. Temperature in Kelvin. And this is how many moles of oxygen I have. Now, step 2, moles of oxygen to grams of oxygen. How do you do that? Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. Where do you get this? 1 mole of a compound equals the molecular weight of that compound. What's the molecular weight of oxygen? The sum of all atomic weights to oxygen. 2 times 16.0, 32.0, and this is the number you get. And this is something you should also be familiar with. Now, one of the things I noticed when I wrote this, after I wrote this, is, oh wait, I see a question. Did I make a mistake? I might have. Let's go back. Wrong thing. Actually, it was the right thing. Hang in there while I check. You're right. I made a mistake, so that problem's wrong. Put this number in for pressure, you'll get another one. And I'm not going to have time to correct it, but over end of the semester break, I'll correct these. Sorry about that. Thank you for finding it, Biljana. Oh, I'm so ashamed. Thank you for helping me. All right. Well, I warned you the first day. I don't walk on water unless it's frozen. And even then I stay off, which means I'm not perfect. And you see once in a while, even Dr. White, there goes my perfect score. But anyways, in that problem set, which I now have to correct sometime in the future, if you look, that's not what I want. Important information, Dalton's law of partial pressures. That's the total pressure of a mixture of gases is the sum of the partial pressures of each of the gases. And the partial pressure is what would be the pressure of that gas in a mixture if it was alone. So Dalton's law, which you're given, P total equals the sum of the individual partial pressures. So since I don't have a problem for you, I better give you one. And there's a problem for you. So you can practice Dalton's law of partial pressures. Everybody see that? Now let me decode it. What is the pressure of a mixture of argon and helium gases if the partial pressure of argon is 602 torr and the partial pressure of helium is 101 torr? Your turn. And when you're done, give me a thumbs up. Remember, Dalton's law of partial pressures, the total pressure is the sum of the partial pressures, P1 plus P2 plus so on. All right, I think everybody's done. Let's do this. So the question is, what are we being asked to find? What is the pressure of a mixture of gases? So P total, the total pressure. What are we given? The partial pressure of argon is equal to 602 torr. And the partial pressure of helium equals 101 torr. And remember, P total equals the sum of all the partial pressures. In this case, that would be P total equal partial pressure argon plus partial pressure of helium, which is 602 torr plus 101 torr. Keep an eye on me, been making mistakes today or in the past, and that would be 703 torr. And that's your answer, and that's how you do Dalton's law of partial pressures. And with that, I will ask, does anybody have any questions about gases and gas law problems? And the answer is, of course, you can see it again. However, it'll cost you $19.95 plus shipping and handling. Nope, because I'm giving it to you in torr. I didn't. And Dalton's, that's a good question. Dalton's law of partial pressures, the pressure can be in any unit you want to use. Since I'm using torr, I'll end up with torr. Now, if I were to ask you, which I would never do, what's the partial pressure in atmospheres, if that wouldn't be real world, and I don't do that on a test. So hopefully it answers your question. Other questions before I move on? Well, I guess not. So guess what time it is? It's lab time. We're going to have a fun, quick lab. Let me just. And this lab, everybody see the Molarity Lab on the screen? Thank you. And this lab deals with molarity. And molarity is moles of solute per 1 liter, but in the lab we use 1,000 milliliters. And it is written as X capital M, then the compound. So if you have 9.45 capital M NaCl bracket AQ close bracket solution, then you have 9.45 moles of sodium chloride per liter or 1,000 milliliters. And the AQ in the bracket tells you the solvent is water. Now in this lab, you'll be making two solutions with obviously different solutes, and you'll be calculating the molarity of each lab. Now, normally this is conducted in what we call a volumetric flask. And hang in there while I Can everybody see the volumetric flask on your screen? Oh no. Let's try that again. Did it work now? All right. And these are volumetric flasks. And see the line right there on this one right there? You put the solid in there, your solute, you fill it up out here, you swirl it, dissolve it, then you add enough water to get it just to that line. And these are accurate to about 0.003% accuracy, which on 100 milliliters is quite accurate. On a liter, it's very accurate. Now, time to show you Dr. White's really a chemist. A number of years ago, I started collecting and putting in a table in my living room, cute little art chemistry stuff. And this is from my collection. This is a tiny little volumetric. Isn't that cute? You can see the line right up here, which you fill it to. And it's got a stopper so you can mix it like this. I got a glass bead in there, but anyways, I also have this is a 25. I have a 10 milliliter, which is even cuter. But not, if I think this is cute, he's a chemist. He's lying to us. But unfortunately, in Beyond Lab Z, and I talked to them about it, for whatever reason, they didn't put in a volumetric. They use a graduated cylinder, and it works, but in real life, you'd use a volumetric. So let's take a look at the lab. And just to remember, key formulas you need to use for moles of a solute, that's grams of a solute times 1 mole of the solute divided by the molecular weight of the solute. I'll call that formula 1. Now, in the lab, you're not going to have it 1,000 milliliters. So how do you normalize it to get the 1,000 milliliters? You multiply the moles of solute times 1,000 divided by the milliliters of solution, and that will bring it up to 1,000 milliliters. And what you're going to do is go through all these steps. And once you get to 13, you'll finish the first solution. Then number 14, you will repeat steps. That should be steps, not sets. 3, wow, I'm going home. Oh, wait, I am home. It's mistake Thursday. 3 through 13 for the sodium bicarbonate. All right. Let me log into Beyond Lab Z. Log into the chemistry lab. All right, now we're going to do something different. Now, can everybody see Welcome to Virtual Chem Lab on your screen now? All right, now normally I'd have you click on something on top. This is different. See where it says worksheets, the lower left, and this is in the instructions. Click on reactions and stoichiometry. Stoichiometry is a fancy way. And now, if you scroll down, see where it has 2 different creating solutions of known molarity. Everybody see that okay? The top one, and if you look over here, it's for ammonium chloride, which you'll do. And the second one you'll come back to is for baking soda, which is otherwise known as sodium bicarbonate. Now, if I click on the first one, it'll open up the actual simulation now. Everybody see that on the lab on your screen? And let me move this up here. Open up the beaker. Oh, it makes noise too. Put the beaker by this bottle, close your drawer. Now, click on the balance, everybody see, and this is in the video, so you can go back and watch it. And then you'll take a piece of this weighing paper, put it on there, and notice I have a weight on there. I don't want that, I want 0, so I will click on tare, and it's 0. Now here's the ammonium chloride. I'll click and open the bottle, take my spatula, oh, and click on the label and put some on there. Come on. Let's try this again. Come on, work for me. I think I'm having a technical difficulty. Worked all right yesterday. There we go. Come on. All right, let's try this again. Say Friday the 13th. There we go. I don't know why I didn't want to do that for me. And notice we have a weight there. You'll record the weight. Now, next, take this and put it in the beaker. Ta-da! And now, let me minimize. We'll zoom out, take the beaker, and go over here to this largest graduate and fill it in. It shouldn't make that noise because it's a solid. I'll have to. I've never heard a solid sound like a liquid. Then you'll take it and you hold under there till it pops back, which means it's full. Now, notice that's a 50 mil full. And does everybody see the lab on the screen now? You put the weight, you have the volume, 50 mils, you can calculate the moles, and then the molarity, you'd use moles times 1,000 divided by 50. And that will give you the molarity. And you do the same thing where you click on for the baking powder, you put the filter paper on the screen, you put the balance, you weigh out some stuff, hopefully without the difficulty Dr. White had. You put it in the volume, do it in the 50 mil, and you calculate the moles and the molarity. And do the questions. And that's the lab. Any questions about the lab? I said it was a quick and easy lab, but it's good practice for molarity. And with that, good news. We're done. Oh, that was strange. We're done. And I can say, gang gesund. Don't forget, on Monday in class, in Zoom lecture, I'll be going through the solutions problem set. Make sure you do those because coming up next Wednesday is test number 3. Test number 3. And with that, I'm done. And I get to say, gang gesund, be healthy. I'll see you on Monday. Bye now.